Hey folks, welcome back to CSE 1322. In today's lecture, we are going to cover Module 8, Part 2, which is going to talk about stacks and queues. So let's start off with stacks. When you think about a stack, I want you to think about a stack of pancakes. Generally, when you cook pancakes, if you've ever done that, you put them onto the griddle, you cook them, and then you put them onto a plate when they're done. And so effectively, you put more and more pancakes on top of the plate as you are cooking them. So the very first pancake that you cook is actually going to be the last pancake that you eat, assuming that you start from the top and work your way down. And that's how stacks work. New things are pushed onto the top of the stack and they effectively push the existing items down below. And so the terminology we use for adding to a stack is actually push because we're pushing a new item on top of all of the other ones. Likewise, the terminology is pop to pop an item off the top of the stack. That's the very first thing. So stacks are implementing a first in, last out behavior, meaning the very first thing you put in the stack is the last thing that you eat, the pancake. This is also known as a last in, first out behavior. And so the most recent pancake that you put on the stack is the first pancake that actually gets eaten. And so basically a stack gives you the ability to item or to put items in and to take them out in an order. Now, in the real world, we don't use stacks in grocery stores or somewhere like that. You'd be pretty annoyed if you got into line for a checkout and they checked out every person who came after you before they got to you. The very first person who walks into the store in the morning would be the last person checked out at the end of the night, which is obviously not useful. That's going to be more of a queue, which we're going to look at here in a few minutes. But stacks are very useful for other things. So when we talked about recursion a couple of weeks ago, you remember we drew an activation stack. And effectively, the activation stack looked like this, where you had your main method down at the bottom. And then when it called something like, do stuff, and it passed it 3, what happened was do stuff happens above it on the activation stack. And you can see this is very much a stack. Then this code executes, and when it's done, it returns back down to the previous level on the stack. New things are added on top as they're added, and only the top thing is the one that we're processing. And then once it's done, we return to the next thing below it, and the next thing below that, and so on and so forth. So stacks are used in computing a whole lot because that is kind of how, well, that is exactly how method calls work. They are implemented as a stack. All right, so let's look at using the built-in stack in Java. So in order to use a stack, you're going to import Java util stack, and then we're going to create a stack just like we create a linked list, just like we create an array list. It's going to be stack, the angle brackets, the thing we're storing in the stack, which in this case is a string, a variable name equals new stack string, and then the parentheses, same as if this said array list or same as if this said linked list. Remember, the thing that's in the angle brackets must be an object. So again, this would be integer with a capital I, not int, and it would be double with a capital D, not double with a lowercase d, or any other type. It can also be a stack of students or a stack of employees or a stack of dogs or any other class that you make. It just has to be an object in here. In order to push items into the stack, as I said, you use myStack, which is the name of the variable here, dot push, and then you give it the item. Of course, the item has to be of the type that you declared the stack to be. So in this case, I'm pushing into the stack item 1, then I'm pushing in item 2, and finally I'm pushing in item 3. And then we have a method called peek. What peek does is it peeks into the top of the stack and tells you what's in there. It doesn't change anything in the stack. It doesn't remove anything or put anything in. It just tells you what's on the top of the stack. Very often with the stack, you're going to want to be able to see what's up there at the top, and that's done with peek. And so if I do peek right here, I'm going to see item 3. And that's because effectively item 1 was pushed in first, then item 2 was put on top of it, item 3 was put on top of that, and if I peek, I'm seeing the thing at the top of the stack, which is item 3. All right, next up I do a string next item equals myStack.pop. So this is the method pop, which is going to take the top item off and return it to you. And so that's going to put into next item, which is a string, the thing that was in the top layer of the stack, which is item 3. So if I print that out, it's going to say next item to do is item 3. That's the same as what peek did, but I need you to understand that pop has actually changed the stack, unlike peek. Pop has removed that item from the stack, and now the thing at the top of the stack is going to be 2. So if I were to print this out, I would get item 3, next item to do is item 3, and then item 2, and that's coming from this peek, tells me item 3. Next item to do is item 3. That's because I popped item 3, and now I see item 2 when I do a peek. All right, so although item 3 was the last item added to the top of the stack, it is currently the thing we see when we peek. That is the nature of the stack. You're always looking at effectively the top of the stack. All right, so how would you go about implementing a stack? Again, you wouldn't. There's a built-in one in Java, so you would just use that one. But if you wanted to implement it yourself, you certainly could do that with a linked list. So let's take a look at that for just a moment. Let me erase my little whiteboard here. And so basically, if we were going to do it with a linked list, we would probably do the push method such that it added to the head of the linked list at the front. So here's my item number 1 that I'm putting into the linked list. If I push another item into the linked list, we'll put an item number 1. That's going to be pushed in on front. I'm sorry, I meant to do an item number 2. That's going to get pushed in on front of item number 1. So this is the same item here as we have here, but it's now got a new item on front of it. That's what happened when I pushed 2. Okay, so that's how I would implement it with a linked list. I would just insert at the front of the list. And then likewise, if I wanted to remove an item or if I wanted to pop an item, so if I do a pop right now, what would happen is it would simply return whatever's at the front of the list, which is going to be a 2, and then it's going to update the list such that head now points to the next item, and that's effectively going to have the garbage collector clean all this up, and now the thing that's left in the list is a 1. So the simplest implementation of this is with a linked list. We simply insert new items at the front of the list and we remove items from the front of the list. And that is what we set up here. That could be done with a linked list. Great. Could you do it at the back of a linked list? So instead of using the front of the linked list up by the head, could you do it such that you add new items into the back? Well, let's take a look at that for just a moment. So we'll start off with a blank list, and we'll assume that we push in a new item into the list. So here's my blank list. So we have head, and it's empty. So I push in an item, and pushing an item into the back of a list versus the front on the first node makes no difference. So effectively adding it in is just simply going to update head such that there's one item in the list, and it's going to look like that. Okay, so now when I go about adding another item into the list, this time again, I'm adding it to the end of the list. So I make my temp, my new node effectively, I put the number 2 in it. And the way that we do this is we update the end of the existing list to point to my front of my temp node. And that's going to make it such that this is now gone, and eventually that will go away, and I'm left with this linked list where 2 is now inside of the linked list. So I can certainly do a push at the end of the list, and that absolutely works. But the question is, if I try to do a pop, how do I do that? Well, if you remember with a linked list, pulling an item out at the end of the linked list is a bit harder than pulling it out at the front. Pulling it out at the front, you just update head, you pull the data out of it, and then you update head. But pulling it out of the back of a linked list, I have to use some kind of a current to work my way down the list until I get to the node that I'm looking for, and then I'm able to remove it. So it's a lot more work if I do it at the back of the list than it was if I do it at the front of the list. And you might say, well, what happens if I have a tail pointer? So I'll make a new list, and we'll talk about what it might look like with a tail pointer. So we have head, and we have, we'll put a few nodes in the list here just so that we can talk about where we are. All right, so in this world, we also have a tail, which is pointed here. Okay, so doing a pop now is easy. I just take whatever's in tail.data and I return that, and then I set tail to null. But if I set tail to null, does that actually remove the item out of the list? No, because the item is still there, because ultimately all I did was I changed tail, but you can see that had no actual effect on the list. So tail equals null isn't actually the right answer. That doesn't solve anything. So how do I remove that last item out of a list if I have a tail link? So we'll go back to having the link like we did before. So to remove that item out of the list, assuming that it's a singly linked list, the tail actually doesn't do me any good. It makes it easy for me to get the data out, for sure. But actually updating tail, the only way I can do it is to start off with a current, point it to the first node, and then use a loop to move it along the list until I get to the node before the last node, and then update tail to there. And then set tails next to null. Tail dot next to null. That's going to have the effect that I wanted. Now this node's going to get deleted. But that was a whole lot of work with this current pointer and me having to move it all the way along the list. The tail didn't really buy me anything. So that's why, remember, at the end of the last lecture, we talked about the idea of a doubly linked list. And if this list had been doubly linked in the first place, then and we had a tail pointer, then this does get a little bit easier. So we're going to do tail here, and this is the original list before we did anything crazy. All right, so now we're going to make this a doubly linked list. So I'm going to put in the reversing arrows back all the way up through the list and set that equal to null. So now it's not actually difficult to remove from the end of the list. I simply say tail equals tail.previous, which is this guy. And so that's going to have the effect of tail pointing to there. And now I can get rid of that last node by saying tail, which is this guy, dot next is equal to null. And the fact that this is still here, linking it back, is irrelevant because there's nobody linking to this for node anymore. It links to other places, but nobody is actually linked to it. So what's going to happen is our happy little garbage collector is going to come along and it's going to garbage collect the end of that list. And now everything is updated correctly. So what I'm telling you is if you want to be able to remove from the end of a list to implement a stack, you can totally do that, but you would definitely want to be in a doubly linked list and you would definitely want a tail pointer. If you have both of those, then it's the same amount of work to delete from the front, to add in the front, or delete from the front, or add in the back and delete from the back. It's exactly the same amount of work as long as you're doubly linked and you have a tail. If you don't have a tail and you're not doubly linked, then it's a whole lot more work to implement the linked list using the back of the list instead of the front of the list. So you'd want to be careful that you choose the right data structure if you're going to do that. But again, in reality, you're going to use the built-in one that Java gives you. So which of these is easier? Well, it depends on whether you're storing it in a doubly linked list, whether you have a tail link. All of those things are going to affect that. But adding something into a stack and removing something from a stack is basically one item of work, as long as you have the right data structure and you're using it as a linked list. Okay, so let's talk about implementing a stack using an array or an array list. Is it possible to do that? Well, let's grab our little window here again, and let's start off by erasing what we have. And so let's assume that our stack is never going to have more than 10 things in it. So I'm going to make an array. I'm going to make it cells 0 through 9. And now I have my 10 cells, we'll presume. I don't know if that's the right number or not. It doesn't really matter. I'm sure it's the wrong number because I'm sure I did not guess correctly. There we go. See, it's perfect. That's where the array always ended, and anyone who tells you otherwise is lying to you. All right, cool. So now that I have my array with 10 cells in it, if I want to implement a stack, how would I go about doing it? Well, it seems like if I put the first item in, I'd obviously put that into cell 0. When I go to put the second item in, it seems like I should put it in the next empty cell along the array. And so the next item will go in here. If I do that, when I take an item out, so if you ask me to pop, I would need to pop it out of the end of the array. So I'd need to pop it out of this cell and then get rid of it. Okay, so usually if I was going to do that, I would keep track of some variable, which would just be an int, and I'd call it last cell or whatever you want to call it. It doesn't really matter. And right now, that would be equal to 1 because the last cell that has actual data in it is cell number 1. And then if I get a pop call, I simply return the array at last cell, and that's going to return for me the number 1. And then I just change last cell to 0 because I've pulled one item out, and now the last cell is really here, not where it previously was. So every time I do a push, I would add 1 to this value. Every time that I do a pop, I would remove 1 from this value. And as long as I keep track of the cell in that last cell, then life is good. The only problems with this implementation, it absolutely can work, is that I have to make an arbitrary limit as to how many items I can ever have in my stack. Now that I say that, I feel like there was an exception that we ran into when we were doing recursion where Java said stack overflow error. And that's exactly why. The limitation as to how big the stack can be in the case of your recursion calls or just calls to methods is based upon how much memory is allocated to your process when Java starts up. And once you exceed that, Java crashes because it tries to add something into the cell and there's no room. It's implementing it as if it's an array. So just keep that in mind. But ultimately, this implementation could work. So again, what I'm doing here is I'm asking, could I implement a stack using an array? And the answer is yes, adding the item to the end of the array or the empty cell in the array, the last empty cell, that allows me to keep track of where I am. And as long as I pull the items back out in reverse, I will always get the last thing that was put in, which is what a stack is supposed to do. The downsides of this implementation are just that I have to keep track of the last cell, which is no big deal. And I do have an arbitrary limit, which is how many items I can put in the cell because I had to declare the size of the array at the very beginning before I started. So, absolutely, this works. Everything is good in this implementation, except that I have that limit that I don't have when I'm dealing with a linked list. So, what about putting it at the beginning of the array instead of putting it at the end, which may make a little bit more logical sense to you? I think you're going to see that that's a little bit more tricky than you would think it is. So, to be clear, instead of putting it in at the end of the array, I'm always going to put the new items in at the beginning of the array instead. Okay, so here's my array 0 through 9. And the idea is I put the first item in cell 1. That's not controversial. That's what we would expect. But what I'm suggesting is instead of putting the new item in the first empty cell, I'm going to always put it in cell number 1. So effectively, what I'm going to do is I'm going to move that guy down and I'm going to put the new guy in cell 1. In cell 0, I mean. Okay, this works, but it does have an issue, which is that each time I add a new item in, I effectively have to move everybody down to make room for the third item that I now want to put in. And that moving of stuff down is work. Like, so to add in my fourth item, you notice that I have to move that guy to there, and this one to here, and then this one to here, and now I can put the new item in to the beginning. And so the one goes here. Yikes. Cannot find the eraser suddenly. There we go. The 2 goes in here. The 3 goes in here. And now that I've moved everything, the 4 goes in there. So that's a lot of work. And I'm not really sure what I gain from doing that. I don't have to keep track of the last cell anymore because the new item that is the top of it is always in cell 0. And logically in your head, that probably makes more sense that it should be in cell 0 rather than it's sometimes in cell 4 and sometimes it's in cell 5. So logically, this makes more sense, but based on the amount of work that you have to do to implement it, it's actually worse. So generally, you would not implement a stack in this way because it's too much work to have to keep moving everything around inside of the array every time you add something new in. And instead, you would just use the back of the array. If you do this, how much work is it to add in one new item? Well, it depends on how many items are in the array. If there's nothing in the array, it's one operation. Just insert the new item. But as at the moment, there are four things in the array, so inserting the next thing is going to take four operations to move those things, plus one operation to insert the new thing. So it's actually n work if n is the number of items in the array. And again, this doesn't really matter as long as there's 10 things in the array. Nobody cares. That'll take 10 3 billionths of a second. Cool. But if there's a billion things in the array, then all of a sudden it takes a second to insert something. And you might say, well, even that's not so bad. But like a second is a long time when you're waiting for a window to refresh in an app. That feels like a long time. So all of a sudden, this implementation doesn't really scale. It works as long as we have a small number of things, but the moment we start getting into large numbers of things, it becomes kind of inefficient. As a matter of fact, the more data that I store in this app, the more inefficient it gets. Whereas if I just implement it the other way, where the number is at the end, the efficiency is the same. It's always one work to insert and one work to remove, regardless of how many items are in the array, as long as we're using an array that's big enough. If we're going to grow the array, then we've got a whole other problem that we're going to have to deal with. Okay, so again, if you wanted to use a stack in your program, you would actually just use the built in stack in Java, and you would do it like that. Under the covers, that stack is implemented with code. And it is possible that it's implemented with a linked list where you insert and remove at the front of the list. It's possible that it's inserted in a doubly linked list where you insert and remove from the end of the linked list, and that would work fine. It's possible that it's implemented in an array, but if it is, it's probably implemented in an array such that we're adding at the end of the array because adding at the front doesn't make sense. So which one is it? Go look at the Java documentation and take a look. Go to Oracle's website and look at the Java documentation, and you can see which one they chose, and you can see the actual source code for the implementation for it if you look for that. Because all of the code for Java is actually open source. You can see how they did the implementation of the libraries. So that is a linked, that is a stack. In general, putting something into a stack, and we talk about big O as a measure of how much work it is to do something. When you insert something into an array, the big O of putting it in the array is one operation. Always takes one operation to put something in an array. You never have to move anything or anything else, just put it in the array at cell 3. Life is good. If you try to insert something into a linked list, putting it at the front of the linked list is likewise order 1. It just takes one operation in order to do it. But if you need to insert at the end of a linked list and you're not doubly linked and you don't have a tail, then it's n. It's however many items are in the array. And so the idea of big O, it's a way for us to measure how much work it takes for an algorithm to get something done. We're not giving it to you in a number of seconds because the number of seconds is going to be determined by the hardware. If I have a processor that's running at 3.8 gigahertz and you have a processor running at 1 gigahertz, it's going to take a fourth as long for my machine to do it as it is for yours to do it. So it's not useful to talk about number of seconds. So instead, we use this big O notation as to how many operations will it take. And the way that big O works is you're not really caring whether it's 17 versus 19. That doesn't really matter. We're talking about orders of magnitude, and that's where the O comes from. It's how many orders of magnitude of work is it going to be? Are we doing one operation always, no matter what we're trying to insert and how much data there is? Or are we doing n operations, which will grow depending on the number of data points that are already in the data structure? So you've seen order 1, you've seen order n. We've talked a little bit about big O before when we were dealing with sorting an array. We talked about how bubble sort and insertion sort and selection sort, which were types that we mentioned in 1321, those are not very efficient. They're considered n squared algorithms because it takes n squared operations in order to sort the array using them. But something like merge sort, which we talked about when we were in recursion, or quick sort, which is a derivative of merge sort, both of those are considered n log n, which is significantly better than n squared. So you've already seen a couple of big O notations. You've seen order 1, which is the best case scenario, and it's what we always are hoping for. Order log n, which is worse than order 1, but it's better than order n, because log n, it's log base 2 of n, that's going to be a smaller number, and that's good. Things like a Search, where you're doing a binary search, where you get to throw away half of the options each time, that's considered an order log n algorithm. The next step up from that is going to be n, which means that you are going to do a linear amount of work based on the number of items that are in there. After that, you have n log n, which is the next step up. And then you get to things like n squared and the n or n factorial, and those are all much, much worse. And we do certainly have examples of each of those, but that's not where you want to be. When you're dealing with a data structure, it's interesting to ask, what is the big O of putting something into the data structure? What is the big O of getting something back out, like searching it for an item or removing something from it? And then also, what is the big O of searching it or sorting it? Those are also big, interesting questions. So, with an array, we've talked a little bit about the idea that putting into the array or taking out of the array is order one. It's very, very easy. You just specify which cell you want to do it to. If you want to look through the array, the best that we really know how to do is order n unless the array is sorted. If it's sorted, you can get down to a binary search, and that's log n. But if it's not sorted, then you just have to go and look in every cell and see if you found the thing you're looking for, which is n. Sorting it takes n squared or n log n, depending on the algorithm that you use, ideally n log n, which is still a lot of work. And if you're having to sort it every time you add something new in, then all of a sudden that's a lot of work. So you might be able to trade that and make it so that when you add the new item in, you put it in the correct spot. Well, it's no longer order one to do that because now you have to find the correct spot, which is probably going to be log n because it's a binary search, and then one to add it in. So that's going to be a log n to do an insert, but that keeps your array sorted so you don't have to spend n log n to resort it. So these are the trade offs that you're going to have to start deciding on. And again, yes, you always want to have an order one operation if you possibly can. And that would be great if in the world you could always have order one, but you can't. Anytime that you have order one for an insert, that probably means that your deletes or your sorts or your searches are going to suffer in some way. And so you have to make those decisions as to which way you want to go. As far as stacks are concerned, depending on the implementation, it's fair to say that in general, if you do a good implementation, your insertions and your removals, which are known as pushes and pops in a stack, are going to be order one operations, as long as you implement it in a good way, like we've just described. Um, so that brings us to our next data structure, which is going to be a queue. A queue works the way that you would think about when you're in a grocery store or in a department store or whatever kind of store that you're in and you want to go to get checked out. Generally, the way that that works is the first person who gets in line gets checked out first, and the last person who gets in line is the last person who gets checked out. So a queue implements a first in, first out. That is different than a stack, where it is first in, last out, or last in, first out. It's the opposite of that in effect. In a queue, we deal with the methods enqueue and dequeue as opposed to push and pop. These are just names. It's just convention that we call it enqueue and dequeue rather than push and pop. But they add and remove the data from opposite sides of the data structure. So inside of Java, we have many implementations of a queue because it turns out there are different types of queues that you might want. So the most basic type is called an array dequeue. The actual queue object, it's not really an object, it's actually an interface in Java. And then you have to use one of the children of it, of which there is array dequeue, there's priority queue, and there are some others as well that you can see if you go take a look. But each of these has their own different ways of doing things. Array dequeue works like a basic queue. And so pretty much what you do is you do an add to put things in, you do a remove to take things out, and you also have a peek that'll tell you what the next item is. So if you do these examples here where you add in item one, then item two, then item three, just like in a regular queue, the thing that you added in first is going to be the first thing that's dealt with. So when you do a peek, you see item one because that's the first thing that was put in the queue. If you do a remove, you get item one, and now the first thing in the queue is number two, which is item two, and that's what you're going to see. So if you look at the output of this, you get item one, and then you get item two. They come back in the same order that they went in, unlike a stack where they come back in the reverse order. Okay, so looking at the implementation here, again, you would just use the built-in one. But if you were going to go implement it yourself, then we could talk about doing this with a linked list. So one way to do that would be you would enqueue at the front of the linked list and dequeue at the end of the linked list. And again, assuming you have a doubly linked list with a head and a tail, then enqueuing and dequeuing at the opposite ends is order one, and that's very efficient. If you want to do this with an array, it gets a lot more tricky because you would have to enqueue at the back of the array and dequeue at the front. So we know that using the back of the array or the end of the array, the numbers that are 3, 4, 5, that is the better option because you don't have to move everything. But unfortunately, with a queue, no matter what you do, no matter which way you implement it, you're going to end up moving everything in the array one way or the other. So if you enqueue at the back of the array, every time you dequeue at the front of the array, you've got to pick up everything in the array and move it forward so that you know when you do the next dequeue, it's in position 0. If you do the reverse, then when you're enqueuing, you've got to move everything down before you can do the enqueue, and then you can dequeue at the back, which is order 1. So in the case of implementing it with an array, it's going to be order 1 in one direction for enqueue, or DQ, and then it's going to be order n for the other direction, which is enqueue or DQ. So what I mean by that is if you do it at the back of the array, enqueuing is order 1, but DQing is order n. If you put it at the front of the array, enqueuing is order n, but DQing is order 1. So you can choose which one to prioritize. Whichever one makes the more sense based on what you're doing would be the one that you would give the priority. Or better yet, you just do it with a linked list, and then you don't have to worry about it because it's order 1 either way. So an array or an array list is really not the best thing to implement a queue with because you have to move everything around. All right, there is another type of queue that we're going to briefly mention, which is called a priority queue. In the real world, you don't always implement things like a grocery store where everybody gets in line and the first person in line goes first. If you think of something like a hospital ER, you actually process people in the order that they are most severe. So the patient who comes in with a boo boo on their finger, they're going to be the last person that you're going to look at. You're going to deal with the heart attacks and the people who have other major problems first because they're more important that they get to see a doctor first. So that's an example of a priority queue. Yes, if everybody were equal, a priority queue is just a regular queue. The first person in is the next person you deal with generally. But in the real world, there are other things that can influence that. And so in a priority queue, in addition to the data that you're putting in the queue, you generally also put in a priority, which tells it whether it's, priority 1, priority 2, priority 3, or however you're denoting your priorities. In Java, there is a priority queue that exists, and it has methods add, peek, and remove, just like the array dequeue, but it implements it such that you have a priority queue. So something else to be aware of. All right, so in summary, if you're dealing with stacks and queues, effectively, regardless of what the data structure underneath it that you're using is, you're going to enqueue and dequeue from the same side when it is a stack. Or to phrase that correctly, you're going to push and pop from the same side of the data structure when it's a stack. But you're going to enqueue and dequeue from opposite sides of the data structure when it's a queue because you're pulling them back out in the order that they went in. So the first one in has to be the first one out in a queue. In a stack, it's the opposite. So that's the high level difference between the two data structures. Again, if you're going to use either of them, you just use the built in one, but it's important for you to be understanding how they are implemented. They're all just implemented with linked lists or arrays in the backend. So that brings us to the end of module 8.2, and I'll see you guys in 8.3.